Nathan and Brady should be able to hear that. That was as soon as I started recording. Okay. All right. We are going to begin our last section in Unit 1. That comes from Chapter 3. Okay. So just know that when you go to the book assignment and you're in Chapter 3, that is correct. This is coming from Chapter 3. But I want to put it in with all the other limits that we're talking about. Okay, so first of all, I want to talk about a horizontal asymptote. You know what a horizontal asymptote is, okay? It is a horizontal line that our function is going to approach without bound. Now, what I want you to keep in mind about a horizontal asymptote is that it describes the ending and beginning behavior. So it describes what's happening towards negative infinity. It describes what's happening towards positive infinity. It is okay to cross a horizontal asymptote somewhere in the middle of the graph. It just matters what's happening at the infinities. Okay, you may remember that from Algebra 2 and Pre-Calc, graphing some of those crazy rational functions where it did cross the horizontal asymptote. What matters is what's happening towards infinity and towards negative infinity. Okay? So that is what we're going to use it for. All right? Here I have a rational function with this nice green horizontal asymptote highlighted for you. Okay? If I ask you for the limit as x goes to negative infinity, what is happening to our graph as we go towards negative infinity? What is it approaching? 3. The asymptote. So it would be 3. If I ask you for the limit as x approaches positive infinity of this graph, you would tell me 3, because that's what our that's where our function is going. It's approaching 3. It's approaching that asymptote. Now, this isn't the only case we will have as far as limits towards infinity. All right. What we're going to look at, okay, first of all, a limit over an infinite interval is going to describe the end behavior of the function. You can think of it as beginning and end, or you can think of it as end towards infinity, end towards negative infinity. Okay. So there's 2 specific ways we're gonna do this. First of all, we have horizontal asymptotes that are going to tell us what's happening at the beginning and end of our graph. Okay, but not everything is going to be a rational function. A rational function is the only type that is going to have horizontal asymptotes. All right, if it's not a rational function, we would have to look at something else, right? Okay. Sorry, I forgot about this bullet. We have to review a couple things when we get there. But to determine where the asymptote lies, the power of the function has to be considered. Okay? Do you remember how to determine where we have horizontal asymptotes? We have 3 cases. Should we talk about those right now? Okay. You remember them now? You just have to think for a couple seconds. Okay. Actually, before we look at asymptotes, I want to look at polynomials. We're going to start basic. We're going to look at polynomials first. What do I mean by polynomial? Okay, like quadratic, like quadratics, quartics, cubics, these, right? Okay, we have something called the leading coefficient test that describes our beginning and ending behavior. Okay, so please tell me, if we have a positive leading coefficient, what does that mean about our graph? What is going up? Which side? Okay. If our leading coefficient is positive, the right side is rising. Okay. If we have an odd degree function, what does that mean about our beginning and ending behavior? Okay, opposite. And if we have an even degree, we have the same beginning and ending behavior. Okay, so odd, opposite, even, the same. All right. Now, what happens if I go back up here and my leading coefficient is negative? Then the right falls. Why does this all matter? Okay, we are going to be asked to identify limits towards infinity and negative infinity. If it's a polynomial, we need to decide, is it rising or falling at the beginning or at the end? Okay, when we have infinite limits of polynomials, okay, let me rephrase that. If we look at limits towards infinity or negative infinity, our limits are going to be infinite, okay? Because polynomials continue to rise or continue to fall on both sides. Okay, so what does that look like? The limit towards infinity of 2x to the fifth. So positive infinity means the right side of our graph. What is happening on the right side of 2x to the fifth? We are rising. So we are going towards positive infinity. The limit as x approaches negative infinity of 2x to the fifth. What's happening on the left side of our graph? It's falling because we have a fifth degree polynomial. We have opposite behaviors. So this limit is negative infinity. How about 5x to the 6th? If we go towards positive infinity, what's happening on the right side of our graph? It's rising. And if we look at the limit towards negative infinity, what's happening on the left side? It's also rising because we have an even degree. The limit as x approaches infinity of negative 7x to the 4th. And our right side is going to be falling because we have that negative leading coefficient. We have an even degree, so what's true about the left side? It's also falling, okay? This is basically, this is the leading coefficient test. It's just using limits instead of the other notation. Okay? What? No. Okay, so I have a polynomial with more than one term. Does it change? No. Our highest degree is right here, 8x to the fifth. So what is happening towards positive infinity? It is rising. Okay. Don't be fooled. What term do we need to look at?
Negative 14x.
Okay, this polynomial is not in order, right? You need to put it in order. So our leading coefficient is really negative 14 because our highest degree is 6, okay? So towards negative infinity, what is happening in this graph? It's falling. We have an even degree, so both right and left are falling. How do you feel about that? Okay, simple enough. Leading coefficient test. Okay. All right. Now let's consider this. happens if we have a fraction where a polynomial is in the denominator? Okay, what's going to happen? Well, we know a limit towards infinity or negative infinity of a polynomial will be some kind of infinity. Okay, dividing by infinity. That's infinity is you're approaching an extremely large number, right? Yes. Okay. If we have a constant over a polynomial, then as we approach infinity, okay, that fraction is going to go to 0. Right? If we have a constant over a polynomial, we know that that polynomial is going to approach infinity or negative infinity. So that fraction is approaching 0. Does that make sense? Can you accept it? Okay, we have a constant over a really big number. Okay, the bigger our denominator gets, the smaller our fraction gets as it approaches 0. There we go. So the limit as x approaches infinity of 5 minus 2x squared. Okay, what did you say? Confidence.
5.
Talk me through it.
Because when you would plug infinity in, your 2 over x squared would equal 0, which is 5 minus 0.
Okay, so the limit towards anything of a constant is the constant. Okay, now if we plug infinity here, we have 2 over infinity. That is just going to go to 0. So we have 5 minus 0, which is 5. Okay. You're either bored or you don't get it. Bored. All right, let's step it up a notch.
It's too hard.
What? Both.
Okay, so the negative
Okay, here? Well, this is towards positive infinity, right?
Oh.
Here? Yeah, so both of these, they're the same?
Oh.
Yeah, they're both towards, they'll both be 0, because we still have 1 over a really big denominator. In either direction, it's still going to approach 0. Yeah, so that is a very good point. If your denominator is infinity, we're approaching 0 from the right. If your denominator is negative infinity, we're approaching 0 from the left. I like that. Okay. Talk about this one. Okay, so if we look at numerator and denominator separately, we would have infinity over infinity. That's not gonna work. That is not 1. It is not 1. It really is not. Okay? This is what we call an indeterminate form. Okay, and this will come into play later when we talk about limits again. Okay? So we can't do that. No. Instead, this is a rational function. What helps us know the beginning and ending behaviors? Asymptotes. Okay. So here, let's review those asymptote rules. Okay? If the degree of the numerator is less than the degree of the denominator. Can I abbreviate? Is that okay with everyone? Yeah. Where is our asymptote if the degree of the numerator is less than the degree of the denominator? How about y equals 0? if the degree of the numerator equals the degree of the denominator. Okay, you're going to take the ratio of the leading coefficients. And if the degree of the numerator is bigger, what? Then we have a slant asymptote.
Will we ever have big asymptotes here? We'll do that.
There's a possibility. There's a possibility.
Wait, slant among what? What's
I don't even remember.
is there a slant among the graph x equals y, or y equals x? Or
Well, it just depends. There's a slant asymptote. The slant asymptote we find by actually taking the division.
So if it was like 2x minus 1 over 3x plus 1, then it'd be 2 over 3.
What?
I'm trying to think if the degree of the numerator.
Okay, we're gonna go through some examples. How does that sound? Okay, and then I'll show you what I mean.
No, I mean, I know what you're talking about. I was trying to.
You're talking through. Yeah. Okay. So where is the horizontal asymptote here?
2.
It is at 2. They're equal. So our horizontal asymptote is at y equals 2, which means the behavior of our graph towards infinity will approach 2. There's our limit towards infinity. Yes. Okay. Where is our horizontal asymptote? Y equals 1/2. So our limit is 1/2. That's all you do. We have a slant asymptote. Okay, which means our behavior is going to be either infinity or negative infinity, and we need to figure out which one. How?
We're approaching from the left, and
You're correct,
What did you say?
but you
because if you did the division, you get down to an odd function, and then it would be positive odds.
okay. So this is what I want you to do. Okay. What we're going to do is we are going to take each term and we're going to divide it by the denominator's highest degree. Okay. So our denominator is x to the first. So what we're going to do is we're going to take each of these terms, 2x squared over x minus 4 over x, divided by x over x, plus 5 over x.
Oh.
Okay, I'm doing the same thing to everything, right? I haven't changed the value because we're doing the same thing to numerator and denominator. Okay? We're doing this so we can now look at the limits individually, okay? What's x divided by x? 1. So I'm going to rewrite that, okay? If we look at the limits towards, this is negative infinity. What happens to 5 over x?
0.
It goes to 0. What happens to 4 over x?
0.
It goes to 0. So now we can look at the limit as x approaches negative infinity of, this simplifies to 2x over 1. And what is that limit? Negative infinity, we're going towards negative infinity of 2x. Negative infinity. Okay? What? Now, can you think about this step in your head? Yeah, probably. Okay? You're going to find a way to see it without writing this down. So if there is not this work, I'm going to be okay. All right? Don't panic. What? Yes.
Why is 2x approach negative infinity?
Okay. Well, it has a leading coefficient that's positive, so we know the right is rising.
Oh, okay.
Okay. Because now it's a polynomial, right? We can use the leading coefficient test. I'm sorry, I did not say that. I should have. Are we okay now? Yes. Because since it's an odd degree, if the right's rising, then the left has to be falling. And we're going towards negative infinity, that's describing the left behavior.
Oh.
Okay. All right, let's look at this one. Before you panic, sort it out. Okay, we're looking at a limit towards infinity. We have a rational function, so we want to identify the horizontal asymptote. That's all we have to think about. Okay? So, what's true about the degree of the numerator? It's smaller than the degree of the denominator, which means our horizontal asymptote is at y equals 0. So our ending behavior approaches y equals 0. Yes?
I wanted to say you wanted to identify the real leading coefficient of the numerator first.
Well, yeah, we looked at this. It's a cubic over 4 cubic.
You wanted to identify that.
Yes. Yes. I thought we said that. Did we not say that? Okay. Yeah, because I think we said we had a cubic over a 4th degree. Yeah. Yes. Make sure you put it in order. Whether you write it in order or you look at it visually and sort it in your head in order. Okay, but don't get tricked.
Oh, I don't like it. Yeah. See how much okay,
Other equals, then it's like,
the ratio. But also means you add some of those surprises. Yeah.
Okay, let's sort this through. Okay? Do we have a rational function? Yes, we have a fraction. It is a rational function, which means we could have horizontal asymptotes, we could have vertical asymptotes, the whole thing. Well, we do have horizontal asymptotes, we could have vertical asymptotes, okay? Now, what's the degree of the numerator?
1.
What's the degree of the denominator? It's 1, okay? We have the square root of 2x squared, okay? So when we look at our asymptotes, we still have the same rules here, okay? The degree of our numerator and denominator are the same. Now, here's where we have to be careful, okay? We have the square root of 2x squared, and that's how you guys determined that we had a degree of 1, okay? What happens when you take the square root of x squared? It's just x. Okay. So, we're going to have to be careful here. When is it positive x? When x is what kind of values? It's going to be a positive x When x is what?
Greater than -1.
Not quite.
0.
Yes.
Greater than or equal to. I mean, unless you count zero as whatever.
Well,
We count zero as.
yeah, it probably could be. We're gonna leave it out for right now, okay? Negative x when x is less than 0, okay? Why is that so important? Okay, when we look at our horizontal asymptote, where is our horizontal asymptote? 3 over radical 2, or 3 over negative radical 2. Okay? So there's two horizontal asymptotes. When we approach positive infinity, which means our x's are positive, which means our x's are greater than 0, where is it going to approach? It's going to approach 3 radical 2. If we approach negative infinity, which means our x's are negative or less than 0, we're going to approach 3 over negative radical 2.
Got it.
You go back to the previous picture.
Yes.
So this may actually be a little usually, but come over. But look what you just told me.
No, it still does. But what we have to keep in mind is that negative x squared can still be, like, negative x squared and positive x squared are the same, right? And so, that's what we have to take into account up here. Okay.
Then I'm trying to figure out how not to get that backwards, just like actually, hold on, I should write that down actually.
Okay.
I've always been wondering like when plus or minus, it's always been throwing me off because I would always get it backwards talking about whether or not it was the square root of x squared or the square root of x squared or x squared square root.
They all can mean the same thing.
They all can mean the same thing, but one can't have negative x in it, therefore it can't have plus or minus x.
Right. But this one, we can have negative x in it. And so it's okay, right? We can have negative x squared and x squared. So in this case, it's okay. Are you following me?
Yeah.
Okay. Here's your assignment. It's lengthy. Really?
Yeah,
How long did it take us to do those problems?
like 15 minutes.
Yeah.